Okay, so we looked at the 5% rule. We'll look at, we can actually solve for percent ionization as well. Okay, so you looked at the ice table. I'm going to pull it back here a little bit and look at actually solving for percent ionization. So if I look at this example, the pH of a 0.10 mole per liter H3PO4 solution was measured to be 1.70. Calculate Ka and calculate percent ionization. All right, so equation H3PO4 is going to react with water. And that makes H2PO4 negative plus H3O plus. We have phosphoric acid reacting with water to make this. All right, so that's 0.10. That's going to be nothing. These don't start off as anything, right? With the ice table. Now, here's the deal with if we're actually calculating Ka. So we have a pH. So my pH at equilibrium equals 1.70. Okay? So the pH so remember that the pH is a measure of hydronium, right? So the system would have had to have equilibrated to give me this pH value. So the pH at equilibrium is 1.7. The concentration of hydronium, therefore, we can find it. Okay, so the concentration of hydronium equals 10 to the negative pH. So that's going to equal 10 to the negative 1.7. So that equals, when we solve for that, 0.01995. So this increases by a factor of 0.01995. Okay, 1-to-1 mole ratio, so I don't need to carry an exponent down. So this is also going to be 0.01995. And because this is a 1-to-1 mole ratio, this is going to decrease by a factor of 0.01995. And so at equilibrium, it's the initial minus the change. And that's 0.08005. So let's calculate Ka. Okay, calculate Ka here. Ka equals products over reactants. So that's H2PO4 negative multiplied by concentration of hydronium over concentration of H3PO4. So at equilibrium, remember this is my equilibrium expression. So I use the equilibrium concentrations. So Ka equals 0.00497. So my percent ionization, so B, percent ionization, equals concentration of hydronium over the concentration of the weak acid times 100%. So that equals 0.01995 over 0.1, and that equals, right, times 100%. So that equals 19.95 or approximately 20%. Okay. So we can use exponents like x, and we can also solve for the Ka if we're not given it, all right? So we can solve for concentration of the reactants and products. We can also solve for Ka and percent ionization. That's what that shows. Okay, let's look at one more example here, and then I'll end this lesson. Okay, so boric acid, which is H3BO3. Used for contact lenses. Has a concentration of 0.10 mole per liter and a pH of 5.16. Do the same thing, calculate the Ka. And calculate the Ka and calculate the percent ionization. Okay, so again, first thing we do is make the equation. So H3BO3 AQ plus H2O makes H2BO3 negative plus hydronium. And that's 0.10. I don't worry about that. These are 0 and 0. All right, so let's solve for the concentration of hydronium. So concentration of hydronium equals 10 to the negative pH. So that's 10 to the negative 5.16. That equals 6.918 times 10 to the negative 6. All right, so that's going to be plus 6.918 times 10 to the negative 6. This is a 1-to-1 mole ratio, so this will increase by the same factor. And this will decline by the same factor. So my equilibrium values are going to end up being 0.099993, 6.918 times 10 to the negative 6, and 6.918 times 10 to the negative 6. All right, so let's solve for the Ka. So calculate Ka and calculate percent ionization for these examples. Ka equals the concentration of H2BO3 negative multiplied by H3O plus over the boric acid. So that will be 6.918 times 10 to the negative 6. And I'm just going to simplify this. That's squared over 0.099993. So that equals 4.79 times 10 to the negative 10. And that's my Ka. My percent ionization is the concentration of H3O plus over concentration of the weak acid times 100%. And that equals 6.918 times 10 to the negative 6 over what we had initially, which is 0.1 times 100%, and my percent ionization is 0.0069%. Okay, so we're going to end that lecture there. I will post this with for Ka questions, and then we'll do another lecture on Kb. All right, that is it for today.